Getir. Very last day. Getir, this getir. The last day of the week. Getir. Getir. Böyle. Böyle. देखी बोल.
Hello, hello Abdul. Hello, can you hear me? So here I am discussing week 2 assignment and I'm already on question 3. So the question was, in the TCS PC experiment, the TAC range was 100 nanosecond and the number of channels or the number of bins were 4000. So what is the temporal resolution, and from the given option which will have the same temporal resolution as this the 100 nanosecond tag range and 4000 channels. So how do we calculate temporal resolution is the given tag range and the number of divided by the number of channels. So if you do that, we get 25 picosecond. That is the temporal resolution. That is the minimum time which you can resolve. So from the given options, I will do the same thing. Tag range divided by the number of channels. So I'm getting for first option, I'm getting 0.1 nanosecond. For option 2, 25 picosecond. For option 3, it's again 25 picosecond, and option D, it's 6.25 picosecond. So from the resolution, you can see option B and C are the same resolution, which is 25 picoseconds. So this one and this one is the same resolution as the given uh, tag range, 100 nanosecond divided by 4000. So the correct answer will be B and C. Did you get this? Hello?
Yes, ma'am. Yes, ma'am.
Okay. You have already solved the assignment, right?
Yes, yes.
Okay. So let's move to the next one.
Yes.
Now the next question is about the constant fraction discriminator. So from the lectures, what did you learn about the TCS-PC setup and the constant fraction discriminator? Anything can you recall?
Constant fraction discriminator.
Yes. So a constant fraction discriminator. So just simply tell me about the TCS-PC setup, which what have you understood from that?
Uh, Ma'am, this is the kind of measurement through which we can measure the lifetime of a given sample,
Okay.
and that is from 100 picosecond to down the line 100 nanosecond,
Hmm.
and and we are basically using one diode laser. Um, and there is a one TAC that is called the time to amplitude converter.
Yes.
Converter. This is
Yes.
based on the principle of rotating the capacitor.
Yes.
CFT, which is called the constant fraction discriminator. This is basically purpose to actual the pinpoint of the actual arrival of your signal,
Yes.
and um, um, this is very important concept that CFD, because unless uh, you have measured it, you cannot get the actual arrival time to the start or the stop knob. So
Yes.
from so this is very useful to get that precise um, time
Timing.
delta t. Huh, so this is required for the precision time measurement of that particular species or the
Yes.
lifetime related.
Yes, whatever you said was correct only. So constant fracture discriminator is a instrument in the TCS-PC setup which takes care of the timing information of the photon pulses. Okay, so if two photon pulses which are coming at the same time, they should the capacitor should get charged to the equivalent amount if they are coming at the same time. But there can be cases where Like if one photon, they, though they have been emitted at the same time, but in the detector, or like in uh, before they get detected, there can be delay in the signal.
Okay.
Okay, or in the PMT there can be the delay in the amplification. So suppose if one photon is equivalent to 1 lakh electrons, like current 1 lakh electrons, but it may not be the case that every time one photon will give 1 lakh, exactly 1 lakh electrons. Okay, this depends on the efficiency of the detector. So
Okay.
to
But
handle
ma'am,
that, yes.
we are using the same detector for measuring that signal, no? So the responses could be linear, no? Matlab, otherwise,
Yeah, it should be exactly the same, but it it will not be exactly the same all the time. So suppose the detector will be like something like this, the photo PMT detector.
yeah.
It amplifies the signal, right? So it will have mirrors inside, like this.
Ma'am,
So
this is not mirror. This is called dynode.
yes, yes, the diodes. So the when one photon hits it, it gets reflected multiple times, and it gets like this, it will get multiplied. So
Ma'am,
depending
I-
upon the position here, depending upon the position and how many multiplication this photon experiences, like how many electrons are ejected when this single photon hits it, it may vary little bit. So the equivalent amount of charge which has to be generated by the capacitor will not be same every time. So
oh,
this instrument, this constant function discriminator, is used to rectify that error
okay.
which comes in the charging. So if two pulses which have the same ejection time, like same time when they have get emitted, they should charge the capacitor like equivalently.
Okay. But equally, that capacitor should be charged. No, matlab,
Yes. So the
okay.
start and stop should be same for that two photon pulses, if they both are getting ejected at the same time, right?
Yes,
So
yes.
it is multiple experiments going on in TCSPC, as you know. So when one at one point, when suppose the one photon which came at 3 nanosecond, again if
Yes.
the same time photon is coming 3 nanosecond, then the capacitor should get charged equivalently to show the time as 3 nanosecond. But it may not be the case always. Because of the electronics involved, there will obviously be error in these things. So this constant fraction discriminator is an instrument to handle that part.
Okay. Let me ask one very simple question. That your instrument called CTS, no, time related single photon counting, no. So
Yes.
is it truly measure the single photon?
Yes.
Uh, yes. Okay. Okay.
Yeah, we measure only one photon at a time.
Okay.
Yes. So the detectors will be such that it will measure only one photon at a time. There are some, uh, have you heard of these SPAD detectors?
Detective, no.
No, you can Google about it. It is single photon avalanche detectors, like that. It is the full form of that. So these detectors detect only one photon at a time.
Okay. But ma'am, actually, when I my excitation pulse, matlab, how do we how do you ensure that one single photon is emitted and that photon is detected by your detector? Matlab,
Okay.
I have a doubt that I have a doubt that
Hmm. Yes, yes. You ask your question first.
I have a doubt that my diode laser has a sufficient intensity that may focus large number of molecules to the next excited levels.
Yes.
And and that molecules, by virtue of their spontaneous decay, they may emit. Okay,
Yes.
so that process involved a large number of photon emission. So my question is, how do you ensure that one single photon is emitted and that single photon is detected? Actually, I have a doubt, but I never understand that process, how a single photon can be measured. Matlab,
Okay. So the whole idea of the TCS/PC is this question only, that we have to detect only one photon in an experiment. Okay. So
yeah, ma'am.
let me. Okay. Suppose you have your laser source here.
Correct.
Correct. Then somewhere you will have your sample. Okay.
Yes,
It should
yes.
go and hit the laser will
Sam,
go and hit the sample 90
correct.
degrees, and detection will be like this. So before here something will be there, your monochromators and those things to select the
Correct.
wavelength and all.
Correct.
Okay. Then you will have the detector.
Okay.
Okay.
Correct.
Now
Yeah.
when laser can have delay to delay the next pulse. Delay, why this delay? So after how much time, laser is a pulsed laser here, okay? So
Correct.
delay
Yes.
will decide after how much time, or it will decide the repetition rate.
Correct.
After how much time the next pulse should go. This depends on the lifetime of your sample.
Okay.
If you will send, okay, one more slide here. If your sample's lifetime is 5 nanosecond, suppose,
Correct.
and
Correct.
you are sending two pulses which are 3 nanosecond apart, okay?
Okay. Okay.
One
Yes.
pulse, another pulse. So
Yeah.
this time is 3 nanosecond apart, but your
Okay.
sample's lifetime is 5 nanoseconds. So the decay will not be over, the decay will be going on, and in
Correct.
between you will have another pulse. So
Correct.
this
Correct.
pulse excited it here, but since the decay has not completed, there is one more pulse coming over here. So it, the some population which have already got de-excited can get excited again and will show another decay here, right?
Correct. Correct.
So
Correct.
we always, we, to make sure that the this kind of pulse, this is called pulse pileup effect, if this kind of thing should not happen, we need to have the repetition rate, or the time between two pulses should be around 5 times the lifetime of the sample.
Okay. Okay. But how do you come to know the what is the lifetime of your
So
sample?
the lifetime, yeah, you can ask that question, because we are we are measuring the lifetime only, but how do we decide this? So you can have an estimate. Suppose you have some, it will be in around nanoseconds, right? It will be in around some, if it is in tens of nanosecond, you keep your TAC range in hundreds of nanosecond. Okay.
Okay.
So like that you can decide, if your lifetime is in hundreds of nanosecond, you keep your TAC range in microseconds.
Okay.
Okay. So this is the thing, this is what we use delay for. Next next thing is, this will decide the stop and the start. This is what we call the TAC.
Yeah.
Okay. And CFD comes over here, and this also, here also one delay will be there for the emission. Now what happens, start signal is given by your emitted photon.
Correct.
Okay. Here,
Yes.
some part of the laser, which is called the sink, like very less intensity, will go to the tack. Okay, most of it will go and excite your sample. You will get the first photon. Okay, the first photon will come here and it will start the process. Okay, it will start the timer, the clock, stopwatch, and
Correct.
until and then the next pulse, until the next pulse comes, that will act your stop. So you
Okay.
will know that how much time it took for that photon to reach the tag,
Hmm.
or what was the lifetime of that photon.
Yes, but ma'am, actually, but how much power you put into the sample? Laser power, diode laser power.
Laser power will be in pulsed laser. Power also, power can be decided based on that we need only 1 to 2% of the photons, emitted photons. So we adjust the power accordingly. The software shows whether you are within 2% or you are in more than 2%. If you are more, then you decrease the power.
Okay. What is that value? 1 to 2% photons means.
1 to 2% of the photons only should get detected, because
Okay.
as you said, when you will excite the sample, it is first of all pulse laser, lot of photons will get generated. Okay,
Correct.
but
Correct.
that may also saturate the detector, because we are
Correct.
doing this experiment millions of times, at least thousands of times it will take to generate one decay, lifetime decay. So if that many photons are coming continuously, it will saturate the detector and it will not give any signal after that. Okay, and
Correct.
also to get a probabilistic picture, suppose if you will count, let's say you take 100% of the photons every time. Okay, what
Correct.
will happen, that from those only mostly you will get the fast photons. Fast me fast fast photons. So the photons whose lifetime are less, those will come most of the times. But when you will block the block 98% of the photons, you will have a probability that you have blocked the fast photons, because fast photons will be moving fast. So when you will, suppose there are many what we call sprinters running over on a racetrack, and you dig holes in their racetrack. So who will fall first? The probability of the fast runners falling in the hole will be more, right, than the slow
Mhm.
runners. So it is
Correct.
the same case. So the photons which are moving faster will get stopped when you use 1 to 2% of the photons. So to generate the decay is like this. Anyway, the probability of the later photons here is less, and if we use all the fast photons, we will never get the decay, we will only get the photons in this part,
Yes.
right? So
Yes.
this is a to get the probabilistic nature of this decay plot, we set this range that we will detect only 1 to 2% of the photons, and also not to saturate the detector.
Ma'am, that part I can understand, but may I ask you very straightforward question?
Yeah,
Uh,
yeah.
uh, let's say कि my laser power is such that अच्छा, can you please tell me how many photons for a given diode laser pulse a sample can generate?
Okay, that will depend upon the quantum yield of the sample. If the quantum yield is 100%,
Yeah.
okay, so how many photons you will excite it with, you will get that many number of photons.
Okay, that means that number is in millions, I think,
Yes, yes, yes.
but still you can count only one single photon, and that part I can't understand. Matlab, how that?
Okay, so this start and stop is the timer which stops the detector at that point. As soon as the first photon comes here, okay,
Yeah.
it will not detect the photons coming after that.
Okay.
That will be the dead time of the detector. It will not
अच्छा,
count.
अच्छा, अच्छा. Okay, actually, the process is that you are exciting your sample with a diode laser, and as obvious, it can emit the millions, billions number of photons. That doesn't matter to us
Yes.
because or start and stop that may decide which photon comes in a different repetitive experiment. No.
Yes. 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 Yes.
Okay, okay. अच्छा, okay, ठीक है, मतलब fine, fine. That is okay. हाँ. Like it is not that only one single photon is emitted from the sample. The sample may emitted as per their quantum yield of efficiency. It may
Yes.
emit
Definitely.
millions and billions of photons. But
Hmm.
as our system is designed such a way that we can once we can identify one photon, first photon, maybe that
Yes.
is slow, delayed, whatever maybe as per
Yes.
their
Yes.
process signature, the
Yes.
system is automatically stopped.
Yes.
Okay, okay, ठीक है. Okay, ma'am, done. Done, done. Fine. Thanks.
Yeah. Thank you for the question.
Yeah, ma'am.
Uh, Yeah, so here we were discussing about the constant fraction discriminators. Actually, the if you will go into the mechanism, it will be very difficult to for me also as well to explain. But what it does is simply if you have two photons whose signals are who like they got emitted at the same time, but they have different amplitudes. Amplitude in the case, the capacitor which got charged was different for them. So this instrument, constant fraction discriminator, what it does is it equalizes them. So
Correct, correct,
it will
correct.
do some mathematical fittings and all, and it will equalize the charge generated for the photons coming at the same time.
Yeah,
So that we can get a precise timing information,
correct.
which in this case will be wrong. It will show that this came first and this came later because it got charged less, or depending upon the mode, forward mode or reverse mode. Depending upon that, the charges will be uh, the capacitor will get charged differently for these two, but since the photons came together, the charge generated in the capacitor should be same. Okay, so the answer for this question is I think D. It provides the precise timing information, and also there is something to do with zero crossing pulses, which is C. Zero crossing pulses is I don't think I can explain it properly because I also have little doubt in this, but
Okay.
zero crossing pulses is based on the mechanism of these CFDs. So, as I told, if there are two pulses which were coming at the same time, but the capacitor got charged differently, and then the CFD sets a threshold. This is your threshold. From the threshold, this is time. So you see, this is coming first and this is coming later. Okay, so after the CFD's instrument part, it happens something like they take some around 66% of this pulse and 33% of this pulse, and they invert these two pulses and then subtract such that you get uh, you get the start point at the same time. So you get something like this for both.
And
So
I think there is some delayed involved there, ma'am. Actually,
no delay is not involved. Actually, they do the
no,
mathematical part. So
delay,
individually, this is your
the
first,
delay
this is your second. So subtract 66% of this from the first and 33% of this from the second, and then you add the two part. Then it will come something like this, and it will have the same start time. So this is like CFD works like this. I cannot explain it really well because I also don't know much about the instrumentation inside the CFD. but something like this happens. So it generates the pulses which will have the same start time, so that the end product is like this.
Yeah.
Okay, so this is called zero crossing pulses. So it generates zero crossing pulses.
Yeah. Yeah.
Okay. So the question which I just explained is this, that in TCS-PC, number of emission events recorded is limited to 1 to 2% of the excitation event in order to avoid the pulse pile-up effect and retain the probabilistic nature of the histogram. Is this fine, or do I need to explain this again?
Yeah. Okay. Okay. Okay.
Yeah. At the heart of time to amplitude converter, which is the TAC, lies a capacitor. Okay, so
Yeah.
depending upon the time the photon arrives, the capacitor gets charged equivalently,
Yes.
and the charge decides the time part. So there will be some kind of calibration that how much charge equates to how much time delay, and from that we can back calculate the time at which the particular photon was emitted.
Correct.
Okay. Iterative reconvolution is necessary during TCS-PC data fitting because the excitation pulse. Now, the same thing which I explained here. Okay. Now, this pulse which is shown here. Okay, I'll explain it again here. Hmm. So the pulse is not a delta pulse. It will be like this. It's not a sharp like a delta pulse. Okay, so it's
Yes.
again has some temporal width. Even the FWHM in the wavelength scale will be some 60 to 80. Okay, not in the wavelength scale, in the,
Nanosecond.
yes, picoseconds. In the temporal scale it will be 60 to 80 picoseconds. Okay, so when this part will hit the sample, there will be some population which will get excited and start decaying. When this part will hit the population, there will be some population of the sample which will get excited. And most of the part of the sample will get excited when this peak of the pulse hits the sample. So each time you will have a decay. Like each point of the pulse will give a decay like this. Okay, so one single pulse can give rise to many decays. Now in this side also you will have something like this. Okay, so this was your pulse, and each portion of the pulse will give rise to a decay, which is, but we want a single decay for one single pulse. So this So like back calculating one single decay from these many decays is called the iterative reconvolution, which the software does on its own. We don't need to do anything in that. We will simply fit the data, and the fitting method is called iterative reconvolution.
Okay.
Deconvolution or reconvolution. Okay, now this method is done because the peak the pulse is not a delta pulse and it has non-zero temporal width. That's why we need to use this method.
Correct.
Yeah. Reduced chi-square and weighted residuals are the parameters of goodness of fit, which is true,
Yes.
are completely unrelated to each other.
Yes.
No, they are related. And this is multiple select question.
Yeah. Yeah.
Do not
No.
depend upon the range of the data fitting. They
No.
they
No.
will they will depend on the range, because you will get the number of data points.
Correct. Correct.
So
That is uh,
this is wrong. Should be considered while data fitting. Obviously, we need to consider chi-square value while fitting the data. They
uh,
are they are related to each other. Weighted residuals you will get from the chi-square. So
mm,
have both of you watched the lecture, and there is a derivation for reduced chi-square and weighted residuals.
okay.
Yeah, you can either watch the lecture, or shall I do it now?
No. 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 That is not it.
Yeah. Okay. So simply, the what happens is when you will fit your decay. So now decay is what, some sort of histogram, right? So this decay is some sort of histogram, and this this histogram needs to be fitted with, suppose, depending upon single exponential or multi exponential, because it's a decay. So how good the fitting is, this my red one is my fitted data. Okay, how good the fitting is defined by this chi-square. Okay, chi-square should be more than 1 and near to 1. Like maximum, the good fit we consider is chi-square should be 1.1 to 1.5, at max 1.5. More than that, it is a bad fit. And you will have residuals will be here. The software will show you the residuals. Suppose, see this part, there is a mismatch between the fitting and the raw data, right? And here there is a mismatch. So what the residual will show, it will show you a mean line around 1. And since this part it has a mismatch, it will show you something like this. Okay, and then it will be average over here, average. Then this part is a mismatch, so it will again show you something like this. Okay, so this shows you that from which portion you are deviating from your raw data. The fit is not good at which portions of the decay. So these parameters will help you. It comes automatically in the software once you do the fitting. We just need to click a few buttons to do the fitting. That's all. We don't need to do it manually, anything. It generates chi-square. And but one big point over here is we should never always trust the chi-square value. There can be samples for which chi-square is coming exactly 0.99 something, but you can see the fit and you can say that this is not a good fit, even though the all the data points are at the average point. Okay, so the first thing to judge whether a fitting is a good fitting or not is by seeing, by visual inspection. If all the points are covered by the fit, you say that the fitting is good, no matter how large or how small the chi-square is. But if you have two three similar kinds of fit having different chi-square values, but by visually you cannot differentiate between them, but then in that case you take the that fitting which has the least chi-square, around 1.
Yes.
Okay.
Yes.
Okay, so next question is about the value of reduced chi-square. The reduced chi-square should be, as I told, it should be as close to 1, and it should be little more than 1. because it's something, it's ratio. You might have seen in the lecture, sir has did the derivation. So reduced chi-square is chi-square divided by n minus p, and this is a small number which is around about 3 to 4. So when you will subtract this will be, now this number will automatically come as chi-square by n if you neglect this, and chi-square is given as n, chi-square is proportional to n, so it should be n by 1, it should be equal to 1, okay, but it cannot be equal to 1 because of this factor. This number is there which is in the denominator, so after subtracting this from n, this whole thing will be slightly more than 1, but it will not be 2, okay, it will be not be 1.5, it should be equal to like nearby 1, 1.1, 1.001, like that, small number.
Okay.
Okay, data models that may be appropriate in systems containing several fluorophores. Several fluorophores will have, if there are several fluorophores, you can use multi-exponential fitting, or you can use different lifetimes for all distribution of lifetime. So one fluorophore will have one lifetime, other will have the other, and some other will have other, like it's like that distribution of lifetime. So the answer here will be C and D. So if you have multiple fluorophores, single exponential will never work. Single exponential only works in very homogeneous sample, and if you have several fluorophores, it will definitely will not have a single exponential decay. Stretched exponentials, I exactly don't know what places people use stretched exponentials, but the answer here should be multiple exponential and distribution of lifetime. Multiple exponentials like bi-exponential, tri-exponential, depending upon the number of fluorophores you have in the sample. Okay. So both of you have submitted the assignment, right?
Yes,
Yes.
yes.
Okay. So can you solve this one? Is this a numerical question?
This question I have not been attempted.
Mhm. Okay. The global parameters. So in this lecture, sir has not taught about global fitting and all, na? Or did he? In this week's lecture.
Okay.
So the question is that here we in a protein, suppose this is a protein and it has a fluorophore bound at two positions. One which is exposed to water, suppose here we have a fluorophore which is exposed to water, it has a lifetime of 5 nanosecond in absence of any quencher, and one which is buried in the deep skeleton, so one which is here, it has a lifetime of 15 nanoseconds. Okay, upon titration with Ki is a quencher, this exposed fluorophore is quenched. quenched with Ki, while the buried ones are not quenched. So nothing happens to this. Okay. Now, secondary and tertiary structure of the protein are not affected by Ki. Okay, so the protein does not change its structure. If the protein will change structure, there will be different interaction with the fluorophores, and the lifetime will change because lifetime depends on the environment. Okay. Now, fluorescence decay recording during the titration are fitted globally to by exponential function. Okay, so you have AI e to the power minus t by tau. Okay, this is the fitting by exponential. In this scenario, the global parameters are the parameters which you can fix. So in this case, first of all, this 15 nanosecond can be a global parameter. It will not change. This 5 nanosecond will get changed. Global parameters are parameters which are independent. So first thing will be 15 nanosecond lifetime because it is remaining constant even during the titration. And also this the amplitude, both the amplitude for this will be independent of each other. So you can have A1 and A2 also as global parameter. Only this 5 nanosecond, you don't know how much this will get changed. So you can fix these three. There are 4 parameters here: A1, A2, tau 1, tau 2. Okay. Now these three, if you will fix tau 2, how much is getting quenched, that you can calculate. So we can have these 3 parameters as global parameters. So both the amplitude and the 15 nanosecond lifetime. I think this is the answer, which you can fix for the data set, different data sets. So you know the contribution, initial contribution, and nothing is happening to the 15 nanosecond. So if suppose this is A1, A1 is not changing. Okay, so A2 should also not change because A1 and A2 are normalized. A1 plus A2 should be equal to 1, right? And the question itself says that nothing happens to this lifetime. So 15 nanosecond component is also not changing. So A1, A2 and 15 tau 1 is constant. So only this 5 nanosecond, which is the tau 2, will be changed. Hence you can define both the amplitudes and the 15 nanosecond lifetime as a global parameter. Is it okay?
Yes.
Okay. So this is again a numerical question. What the question is, a fluorescence decay is fit to a tri-exponential function. So now you have 3 single exponential, sum of 3 single exponentials. Okay, tri-exponential. Okay, so we need to calculate, we need to define that the lifetime order of these P, Q and R species. So okay, no. Is the, I think we need to calculate the contribution of P, Q and R fit to a tri-exponential. Okay. Now the here you have lifetime will be tau will be A1 tau 1 plus A2 tau 2 plus A3 tau 3. So if you will do that, what you will get, A1 is 0.5, tau 1 is 0.3. A2 is 0.4, tau 2 is 1, 0.1 into 3. What will be the answer? Can you do this? Is it coming 0.85? So 0.85 is the total contribution. Now if you want to get the contribution of P from the total, you need to do that A1 tau 1 divided by the total. Summation, let me write it as sum of AIGI. So okay, so this is 0.15 divided by 0.85. This will come as 0.176. Next, for Q, A2 tau 2 divided by sum. Now A2 tau 2 was I think 0.4 divided by 0.85. This is around 0.470. And similarly you can calculate for R, 0.3 divided by 0.85 will be 0.352. So which has the highest contribution? Q, then R, then P. But there is no such option. Q, R, then P. Is the question this much only, or there is something else?
Question is this much only. Even I have got it wrong. I did not understand it.
Okay, then the options must be wrong. It will be QRP. The options might be wrong. Abdul, did you do this?
Then last two questions I have not attended. This one I will, because this question I can't understand what actually they want to ask. I have given the first one, but that they have shown it correct.
Sorry, I couldn't get you. What?
Actually, I just blindly gave the first one. P detection
PQR. Okay.
PQR, but I have not derived it. I just blindly picked that option.
Okay. Um, I think the options are wrong here.
Okay, but they have given me one mark for attempting it right.
Yeah, but because the option, this thing is wrong here, so their whatever is the model answer, that will be wrong. That's why.
Okay, that might be. Yeah.
So I think I'm done with today's questions.
Yes.
Yeah, if you guys have doubt, you can ask something.
Yes. It is okay, ma'am.
Okay, then I'll close the session then.
Yeah, yeah. You can.
Okay. Thank you for joining.
Yeah, welcome. Thank you.